So let me go to first slide. So the structure of this presentation is 2 parts, approximately maybe half time each. And one thing I would like to say is that my experience from a previous presentation I had was that I felt like talking into a black hole. So in order not to make me feel very alone, I wonder if you could keep your microphones unmuted unless there is some particular amount of noise in your area, because I would be very happy if you interrupt me when I make mistakes, because I make a lot of them, and maybe I have some serious bug somewhere. So feel free to interrupt me. I prefer to have a little bit more seminar style presentation, if that's okay with you. No answer?
You have to hear me coming though.
Okay, go ahead. You know, if there is a lot of noise, I think we can change this. But so far, I don't think there is any problem with noise. Okay, and feel free to interrupt me if you feel like it. Okay, so here's my first example. Well, first, one more thing I should say. Oops, sorry. This mouse is very sensitive. First of all, I apologize for my English. I have an awful Swedish accent. I didn't think so before, but I heard a presentation. I watched a presentation I did myself earlier, and it was really embarrassing. I can tell you a story which actually I was told by a renowned linguist, Edward Quockenbush. He told me this story, after hearing me, he told me this story about the Swedish thief. I don't know if you heard it. It was about the Swedish thief who was trying to run away from the police. This was in the US. And he was running, and he ran into a store, and he pointed the gun at the shop owner and said, "Hide me quickly, or else I will shoot you." And the shop owner said, "Oh, okay, get into that sack over there." Soon after that, police entered the shop and asked, "Have you seen the Swedish thief? He's supposed to be somewhere here." No, I haven't seen him." "What's in that sack?" the police asked. Just some bells." So the policeman kicked the sack, and from the sack there was a voice, "Jingle, jingle." Okay. Okay, now I could hear someone had their mic on there. Okay, so first example, which I had in the abstract there, buying a house. I think this I didn't intend this to be so serious, but this is actually very serious in Sweden, I think. You want to buy a house, you borrow some money to do that, and then if the market value sinks below your debt, in Sweden you actually have to increase your amortization if it sinks, doesn't have to sink that much, and that can be quite serious, especially for students, I think. So we might want to calculate how long we can keep the house, or if we will have to sell it. So in this diagram here, where the house value is some stochastic process, it's often modeled by that the logarithm of the value is described by an Ornstein-Uhlenbeck process, which is one of the 2 very common stochastic processes in real life. So when this value actually crosses the debt, typically, well, the bank wants us to sell the house, or we have to pay amortization or something like that. So this is one concrete example which I think most of us have faced. So this is a rather unpleasant example. I talk about more pleasant example. Or first of all, we have 2 flavors of these hitting time problems. The previous one had one boundary, and they are called first passage time problems. Then there are problems which have 2 boundaries, and they are called first exit time problems. And these 2 problems are related. The first exit time problem is a little bit simpler, actually, because with one boundary you can have some pathological cases, but we will not go into those. So what we want is something called the survivor function, which gives us the probability that this first passage time is larger than the parameter t. In other words, the probability of staying inside this OK interval, at least until time t. Okay, so here's the second example, which comes from biologically inspired machine learning. And this heap here, that is my view of the learning hierarchy. It is credited to Albert Einstein, who said that there are only two infinite things. One is universe and the other is human stupidity. And he was not sure about the first one there. But I can probably insist that human intelligence is a proof that it should be possible to somehow create intelligence. So in order to understand how we should do that, we need to go really down to start with the biological substrate to understand how neurons work. Traditionally, AI has started at the other end. That's the old AI with logic and reasoning. But it turned out that doesn't work. We have to go to lower levels. The current big hype in AI are these distributed embeddings, which can do lots of things, but I don't think these are really enough. We need to go further down. And so what we really need to understand are how neurons signal each other. Basically, they do that by sending pulse trains, and those intervals can be modeled very accurately as first passage times. And this is a very new result. People have speculated about this, but I'm very happy to say that a paper which I wrote together with a neurophysiologist in Lund was accepted 2 weeks ago, and it will probably soon appear in Physical Review E journal. And basically, its model is fairly simple. We have white noise, send it through a second order low-pass filter, and compare it with a nonlinear boundary, and out we get something which is almost exactly fits recorded spike trains from actual in vivo neurons. And so this is my favorite example, which I've been working on for a long time. And that's the original of working on this hitting time problem too. Okay, so the third example, this is a model problem. That is Joe the mosquito, who lives in the pipe. He lost his apartment because the value of it sank below his debt, so he had to sell it, and now he lives in a pipe. And Joe, he is a little bit confused, so he moves according to one-dimensional Brownian motion. And now Joe wants to calculate how long time does it take him to exit this pipe. Okay, so this is not such a hard problem because the pipe has this definite length. The way to compute this length is like this. If we let this function p be the density function for the mosquito being at position x at time t, then we can compute this survivor function by just integrating it over time. And it's actually well known, has been for about 100 years, that that p satisfies the Fokker-Planck partial differential equation, which in this case is very simple like this. It actually looks the same as the heat equation or the diffusion equation, with the boundary conditions at the top and bottom, which is 0, and we have also an initial condition on the x-axis, giving the which is determined by the initial where the mosquito starts at time t equals 0. So what we need to do is to solve this partial differential equation for a square strip like this. Here's the time axis, and the x-axis here is the position in the pipe. I think you have all done this in your undergraduate years. This is sort of the first partial differential equation anyone is doing. But I will do a little refresher on how to solve this partial differential equation. You don't have to care about the details of the formulas here. It's basically the general approach that's interesting. So our original partial differential equation was without the red part here. What we do is that we put in the red part. We assume that we can write it like this. We actually can do it. And this gives us two sub-problems, an initial value problem, which is the left part of this equation system, and the right part, which is a boundary value problem. Left part is the ordinary exponential, decaying exponential solution. And the right one is an eigenvalue problem, which has the solutions are signs which fit this interval with these eigenvalues here. And we can combine these two into a Fourier series, which is the solution to the whole problem. And these coefficients here, the Fourier coefficients, are derived from the initial condition. Does this look familiar to you?
Yes.
Not very strange, right? So the idea here is that the solution is actually a linear combination of these eigenfunctions to the right part there. Okay, now the Mosquito is evaded, and again, well, he wants to do this habitat carrier. I don't know if there is I checked Google Translate for what's the English for bostadskarriär, but I don't know if there is such a word. Maybe someone who knows English better than me knows that. But anyway, he upgrades his housing to a trombone. Now the problem with the trombone is that the length of the interval varies. So this equation we got, the Fokker-Planck equation, still holds with the boundary, same boundary conditions, but now the boundaries actually vary. So the strip isn't square anymore. The strip is varying. And our old method didn't work. So, and I remember, maybe you also wondered about this during your undergraduate years, is that this is very frustrating because clearly for partial differential equations, the important thing is what happens on the boundary. But if you can't solve it with an interesting boundary, then it's kind of useless. Well, not useless, but it's sort of boring. So what should we do about this? So do you have any suggestions? Now I want to hear. What would you say?
Transform the coordinate systems.
Yeah, transform the coordinate system. That's one approach. More approaches? Any more? I won't hold it against you, I promise.
Maybe you can make it approximate it using piecewise linear boundaries.
Yeah. That's also, that approach is something, if you have heard about the finite element method, you can divide this area into, you can mesh it and then solve the equation for these meshes. Quite a lot of work, but that also works. And a little bit newer solution is something called the boundary element method. You can divide the boundary into elements, and then you can sum those up. It's usually faster. Well, sometimes it's faster than the finite element method, but it uses a lot of memory and it's a little bit awkward. I expected somebody to say we can simulate it.
Yeah, Monte Carlo.
Yes, we can do that. But that is actually, that's simplest, but it takes an enormous amount of time. We have to do a very short time step for this to work, because we have to detect the boundary crosses. So the passages. So actually, I will tell you the answer. Ta-da! Nothing, just keep going. Okay. So after this very serious formal mathematical statement, I will be a little bit more detailed about this. What do I mean by this? In more precise words, if we look at the previous pipe example, we can write it in vector form. You know, it was this Fourier series. We can write it as a scalar product of a coefficient vector and the vector of eigenfunctions. And the coefficients are determined through this vector differential equation, and phi is the family of eigenfunctions to this. Okay, so this was for the previous problem. Now what happens in the new one is that the eigenvalues actually vary with time because the boundaries vary with time. But they are actually, they are basically the same kind of eigenvalues and eigenfunctions because they are along the x-axis. So along the x-axis, the t is constant. So this is eigenfunction expansion despite inseparability. How many of you have heard the words separable differential equations? Not so many, I guess. Some have, I know. Those don't have your mics on. Okay. Well, can we really do this? We're not supposed to be able to do this. People say, basically, this eigenfunction expansion stops when we don't have equations where we can separate the x expression and the t expression. So the question is, can we really find a solution in the form here where we have inserted t in the eigenfunctions? And now I can quote Barack Obama, yes, we can. The only thing that happens is actually that the equation for omega, the Fourier coefficients, is that we need to insert two more terms here. And you can see they contain the derivatives, how quickly the boundaries change. So if they don't change, these terms disappear and we're back at the constant boundary case. These CAs and CBs, they are matrices that depend in a fairly simple way on the eigenvalues. So you don't have to worry about this expression. It is fairly simple to calculate. So what it all ends up is we reduce the problem to a set of ordinary differential equations which can be solved very quickly by any typical ODE solver. And these systems are usually quite well behaved numerically. So here's an example. Suppose that we have this, this is the trombone initially is between -2 and 2, and then someone plays it. The Mosquito starts with Brownian motion here at 0 and moves, and the survivor function, if the Mosquito starts here in the middle, it is the upper one here. The dashed red line is a simulation using 1000 sample paths. The lower one is if the Mosquito starting position has a density function, which is the cosine from 2 to -2. So they are fairly similar, a little bit different. This red one take an awfully much longer time to compute than the black one, which is basically instant. Okay, and these are generalizable to a much more general stochastic processes than Wiener processes and Ornstein-Uhlenbeck processes, which are both Ito processes. There are actually even some Ito processes are even for some Ito processes which are not Markovian, it is possible to use this. If you want to look at the more detailed derivation, so it uses Sturm-Liouville theory. When you apply this, it's not so difficult, but one thing you do need is to find the first few components of the eigensystem. There is a method which is called Plücker transformation, which is quite an efficient method to do this. The eigenfunctions for Wiener processes are the sines, as we saw, and for Ornstein-Uhlenbeck processes, they are parabolic cylinder functions.
Are there some limits on the boundary constraint functions? Can they be discontinuous?
The boundaries, they can be discontinuous, yes. The that I made requires them to be something called regulated functions. They can be finite numbers of discontinuities, and differential functions are included. So that's quite a wide set of functions. But there are some pathological cases that happen for first passage problems. I can go to this one here. The pathological cases for first passage time problems appear if there are sometimes the eigenvalues are not countable. That happens for some cases. Sometimes they can be transformed to cases where they are countable. But the problem if they aren't countable is that we get an uncountable number of equations, which doesn't work, of course. But for the normal cases, we actually need only a few of the first eigenvalues because they usually converge very quickly. Another thing which is interesting with this method is that it's applicable to a lot more than the first passage problems. You can use it for parabolic partial differential equations in general. For instance, Schrödinger equations. And if you want to look in the details, you can, there is a detailed article in Journal of Physics A last year, and there's a link on that on my website, www.drnil.com. Okay, that's it.